Can you see my screen and hear me?
Yes.
Yeah, fantastic. So, hello everyone, I'm still Luca Ferranti and from Aalto University, Finland, and today I will talk about automatic differentiation in Chapel, particularly presenting in practice two approaches implemented. So, no, of course, yeah, okay. So, the talk, roughly speaking, first I will give a short overview of automatic differentiation, like why should we care in the first place, what is it, and then I will present ForwardModeAD, which is a library purely in Chapel for doing automatic differentiation, and then I will talk about Enzyme, which is another library for automatic differentiation and how it can be used from Chapel. So, let's dive in. So first of all, why do we want automatic differentiation? So automatic differentiation, computing derivatives. And before we even go into how we compute derivatives, why do we care about computing derivatives in the first place so much? Well, if you remember from high school, like derivatives are easy to compute. You know, you have a couple of rules. The teacher shows you, okay, when you have product, do this. When you have sign, do this, do that. Couple of rules, do a few exercises, boom, done. Where's the trick? The trick, the problem is that what you do in high school is like very short expression, very simple expressions. However, derivatives, computing derivatives in like big optimization problems, in like solving differential equations, in machine learning, training a neural networks on gradient descent methods, you know, a gradient is just a long derivative. We have huge derivatives with very complicated expressions, a huge number of inputs, and now think about doing that by hand. It feels painful, doesn't it? And well, it would be painful also for the computer if we start doing that in a very naive way. So we want to compute derivatives as fast and as reliably as possible. So let's first see how we would compute derivatives on a computer. Well, here on the left, we have the definition of a simple derivative that you recall maybe from high school. So, you know, we have this limit when h goes to 0. So basically, it's like infinitesimally short step difference in the x direction. What is the corresponding change in the output when I slightly change the input? And we say, okay, probably we are on a computer, we do things numerically. So we say, okay, approximately when h is small enough, we can approximate the derivative with this so-called finite difference. This is basically the definition of limit. Now, this is not the maybe smartest finite difference, it's the simplest one, but just to give the idea. And we're not entirely wrong. So finite differences are known. And now here we have an example of this function. And I start with a reasonably big h, like 10. And the error in computed derivative is awful, of course. Then when I start decreasing the step, so when I start taking smaller and smaller step, as expected, my approximation of the derivative gets better and better. However, at some point we notice that something weird starts happening. So if h becomes small enough, and then I keep going smaller and smaller, at some point my approximation error starts getting worse again. And why is this? This is because if we work with floating point numbers, we have finite precision, we cannot represent real numbers arbitrarily well. We cannot represent real numbers on computers, so we work with finite precisions. And if our step from the previous equation, if our h becomes small enough that it's comparable with the rounding error of floating point number, the accuracy in this expression starts decreasing and things start going south, or well, going north. Look at this graph, and the error decreases and the error increases again. So if we have huge expressions and we want very accurate approximations or computation of derivatives, then we would get in trouble with just finite differences. So enters automatically differentiation. What is the idea of automatic differentiation? As simple as it sounds, is that we want to compute the derivative of code. And this now is slightly different from symbolic differentiation, because when we talk about symbolic differentiation, we generally refer to like mathematical expression, symbolic expressions. Whereas with automatic differentiation, we talk about code. So for example, if I have a class or a for loop, like these programming constructs, I want to also compute derivatives through those. Like roughly speaking, one could say that we want to compile the code to its derivatives. I put like quotation marks because there are some cases where maybe it's not entirely accurate. Cool. Now, let's have a short taxonomy of automatic differentiation. There are in general like two axes when we classify automatic differentiation, like two aspects we can look at. The first one is in what direction we go. So here I have a function, which is a composition of functions. And here I have, so if I write like this with kind of like helper functions to make it a bit more readable, then here I have the chain rule, the famous chain rule of how I would compute the derivative of a composite function. And now we see if we look at this equation, we can compute the derivative going from right to left, which now is called forward, because I go from the innermost to the outermost, so I go forward despite the order in which I wrote it here. Or I can start computing the outermost derivative, so y over w2, and then go inward. So forward if I go from inside out, or backward if I go from outside in. And these are like two ways of how we can compute derivatives, and they have actually affect like efficiency of the code depending on the size of the problem and stuff like that. Then the second axis in which we classify automatic differentiation approaches is depending on how in practice implemented. So we have operator overloading, on which I will not talk in this slide much because it's the next slide dedicated to it, or source transformation. So in operator overloading, briefly speaking, we define a new type which somehow encodes the derivative, more on this on the next slide, and then we overload our arithmetic functions, addition, sine, exponential, blah, 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 whatever, on those new types to also compute the derivative. So it could be thought of more like maybe like runtime approach, where I overload the behavior of my function on this new type. Or source transformation, which may be a bit more intuitive. I like generate a new source code, which is the compile, so I kind of compile my code to its derivative. Okay, so this was a very short overview. Now let's talk about the two implementations that we have, or that I have so far in Chapel. So first one is this ForwardModeAD, which is this library which I wrote in Chapel. So this is fully in Chapel and does forward mode automatic differentiation based on operator overloading. So in our matrix, we have forward mode, so we compute from inside out, and operator overloading. So I overload expressions. And when I designed the library, like my principles, I mean, of course, performance, it's obvious. We are Chapel, of course, we want performance. But aside of that, other principles is that I want it to be easy to use. So it should be like expressive, easy to write, like pleasurable to write, but also should be like easily integrable with other libraries. So as we have heard from like Chris talk, for example, this concept of composability and why it's important in open source communities, that if someone develops library for, I don't know, optimization, they should be able to plug this ForwardModeAD library and play with it and use it for work. And at the moment, it supports like the basic things that you would expect from automatic differentiation libraries. So derivatives, gradients, Jacobians, directional derivatives, Jacobian vector products. And I should mention that when I started writing that, I was heavily inspired by how ForwardDiff, the Julia library, for the same operator overloading forward mode automatic differentiation operates. And before we finally get into the code, I promised last theoretical slide. So what is the gist behind operator overloading, forward mode operator overloading? Mathematically, we can formalize it as defining the so-called dual number that we have here, which you can see kind of looks like an imaginary number, except that instead of the imaginary unit, I have dual unit or an infinitesimal unit, which is this epsilon, which is defined with the probability that epsilon squared is a 0. And now if I start with this definition of dual number, so kind of imaginary number, but with dual part where the square is a 0, not minus 1. I start with this. If I start like on pen and paper writing basic algebraic operations, and now I focus on the so-called dual part, so the coefficient on epsilon. Now, if you look carefully at this, oh, sorry, maybe here it would have been clearer to be a comma for presentation. Yeah, but if you look carefully at this, so f is the real part of f big F, and f comma is the dual part of big F. And if you look at this, they start to remind you, wait a second, I remember this from high schools. That's how you compute the derivatives. It actually turns out, if you go on with Taylor series, blah, 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 that the semantics of a dual number is that if I evaluate a function on function f on this dual number, then I get that the dual part is the derivative. So I want to evaluate it on A, and then, yeah, I was a bit inconsistent with the notation here, I'm sorry. I get the derivative on A times the inner derivative. So this is our chain rule here. This A prime is like the derivative of the inner function, and this f of f prime is the derivative evaluated on the outer function. So this is the intuition. Now, how do we do this in Chapel? Well, we define a new record, dual, and now this is very simplified version, more on this later, but we define this new version, dual, which has a primal part and a dual part. And then we start overloading the operators on this new type, on this new record, so to speak. And so maybe let's start with the second one, because maybe it's a bit more intuitive. So now I have a function sin of A, where A is a dual type. Maybe it would be cleaner if I didn't write with where syntax, but whatever. So here we have function sin, so I would compute the sign when the input is a dual number. And now here I say, okay, now the real part or primal part, I take the primal part and evaluate the function. And now how do I compute the dual part? Well, I evaluated the cosine, which is the derivative of sine, on the primal part, and I multiply by the dual part, which would be the derivative of the inner function. Think of the chain rule. So this dual part of A would come from the previous computation. Now we go inside out, and the previous part would be the derivative of the inner function. And now I construct the dual number with a new real part and new dual part, primal part and dual part. So now this is kind of the rule that we defined for sine of how to compute the derivative. Similar thing for addition, not much to say. The derivative of the sum is the sum of the derivatives. The thing I wanted to highlight is that when I started with Chapel, one thing that really got me hyped and excited is that how powerful where clauses are in Chapel, so that I could define like a clause that either of them is a dual type. And now I have a catch-all syntax where when I have mixed operations like floating point number and dual number, dual float, and float, dual int, and so on, I can automatically then overload primal part and dual part on all the real numbers on the dual numbers, and I get this very compact generic code which covers additional dual numbers, but also mixed case with dual and integer, dual and float, and so on. Cool. Now, short example. How would we code the Newton method using forward mode automatic differentiation? Well, here is the function was root we want to find with Newton method. We set tolerance, and now what we do, x0 would be our initial guess, so we guess our root is close to 0.5, but then we use this init dual to initialize it to a dual number, so that it's 0.5 plus 1 epsilon. So initialize the dual part to 1. And then when I evaluate this function on this input, it will automatically compute the derivative on the dual part and propagate the computation through the chain rule with all the rules for derivative of x, derivative of sine, derivative of log, and so on. And so this dual number will have the value of the function at 0.5 and the value of the derivative at 0.5. And then I can do the update rule of the Newton method that I subtract the value divided by the derivative, and then I evaluate again. And now since x is a dual number, when I evaluate the function it will automatically compute function and derivative. Cool. I mean, limitations, maybe I'll skip this for now. We can chat in some open work, but there's room for improvement. Other cool guy, Enzyme. So Enzyme is this library for automatic differentiation at LLVM code. So it supports both forward and backward mode, and it's designed for high performance. And maybe the first question, why at LLVM? Why is it the right choice? Let me give you an example. Now here we are computing we are normalizing a vector. So we have vector in and we want to compute the normalized vector. And now what I want you to notice is that if you look at this code, you may notice that it's not very smart because it computes the magnitude, the length of the vector every time inside the for loop. And now with compilers, like everybody who is anybody in compilers world would be able to optimize that and figure out, oh wait, I don't need to compute it every time inside the loop. Let me take it out for you so that you don't compute it every time. However, now, if we would first do automatic differentiation with the source compilation, for example, generate new code, the new code may break the structure and the compiler may not be able to optimize it. So enters Enzyme. The idea of Enzyme is that we, instead of doing directly automatic differentiation, for example, from C++ to C++, we and then after optimizing, we first compile to LLVM, optimize the code, and differentiate the optimized code, gaining performance. Yeah. And so that's basically what I did in my experiment with Enzyme. I compiled Chapel to LLVM. So Enzyme is basically like a compiler pass in LLVM. So I called that to differentiate and I resume the compilation. And that's like pretty much literally what I'm doing. The makefile is like 3 lines doing that. So yeah, that was pretty cool. Here is a very short example. I'll try to wrap up in 1 minute. We'll have a couple of questions. So this is like how Enzyme works under the hood. If I give a very short the overview, that whenever we have something like underscore Enzyme autodiff, Enzyme knows that when it sees this function in the generated LLVM code, it needs to replace it with the derivative. And now we have a function that takes the square of a number. And yeah, now we pass a pointer of that function to this enzyme autodiff, and then when I compile, this will compute the derivative of it. So that's like the interface. At the moment, it works only for scalar numbers. So I was actually grappling to Michael that I was like, oh, I feel so like frustrated. I couldn't even get to work with vectors. But then Michael pointed out that vectors are a bit complicated in Chapel, so I don't feel that bad anymore. But it worked with scalars, which is not great, but it's a start. And it heavily relies on C and Chapel interoperability, because I basically took the tutorials for C and ported them to Chapel. I want to support more language features, so it should work with arrays. It should work with more like generic functions, which I have no idea how to do because I don't know like how to convert them to a C pointer, but bunch of work. Benchmark, of course, because there's no point if I do it so poorly that it's slow. So it should benchmark should be part of the design to make sure that it works. Yeah, and also like what is a good interface? Like if I look at this code, I don't want to have to write it manually. So should this like part be generated by the compiler? It's like not clear to me what idiomatic Chapel code or good looking Chapel code using Enzyme should look like. Yeah. So thank you for listening. I have the links here to like the 2 repositories. And if there are any questions, I'm happy to take those.
Thanks, Luca. Let's give Luca a round of applause and get some questions going. Anyone got any questions for Daniel's got a question. Wonderful. Take it away, Daniel.
Yeah, hey, thanks for this presentation. I know you said that the dual number definition that you showed earlier in your slides is kind of not the complete one. But since you know, we were thinking about the compositionality aspect that we got from the presentation prior to this, it seems desirable to me for the dual number to be kind of like a wrapper over a different numeric type that's arbitrary, so that, you know, if you want to compose this with something else, it would, you know, kind of work out of the box. Is that something that you're doing or planning on doing?
Yes, exactly. So that's exactly the slide that I skipped, that I think like dual numbers should be more generic and more like parametric type in a way, so that it would work, for example, like if I have MPFR wrapper and I want to do with arbitrary precision, or like if I implement like my arbitrary number type for like double arithmetic because I need more bits of precision, then it should automatically work with that. Or like the original motivation when I started writing is that I work with like I worked a bit with interval arithmetic, so that if I have my type for interval, and if I can with some abuse of like define interval arithmetic, then I should be able to differentiate a function that takes an interval using the same library by plugging the interval inside as primal and dual part. So yeah, definitely like making it generic, parametric, and supporting different number types. It's something that I think it's vital for the library. Otherwise, it's a bit boring.
Cool. Thank you.
I've got one question. And maybe you explained this, but I just missed it. But I'm just curious about like you were talking about there's 2 options of forward and backward mode. And I'm curious like what led you to choose forward mode as this, and like if there's any limitations or anything about using backward mode instead.
Yeah, so the rule of thumb is that generally if the number of inputs is much bigger than the number of outputs, that you should like prefer backward mode. Like in other cases, like if you have more outputs and inputs, or if the size is equally equal, then forward mode would be more efficient. Which is kind of also like the reason why backward differentiation is so popular in machine learning, because if you think like neural networks, you have like millions of parameters with very few outputs. So in that case, like the number of inputs is much bigger than the number of outputs. In that case, like backward mode differentiation is much faster. So that's, yeah.
Very interesting. Daniel, is your hand raised for a second question, or is it still raised from previously?
It's a follow-up to this, actually.
Okay. Great, excellent.
Yeah, so my intuition is that you can't achieve backward mode differentiation using dual numbers, or like using techniques like this that don't do source transformations. Is that correct?
Yeah, maybe I didn't emphasize in the slides, but yeah, the null number is for forward mode.
Is it true? So could you achieve backward differentiation without doing like source wrangling or like inspecting the AST or something like that?
I'm not sure. I think I've seen like some implementations using like also operator overloading for like backward mode, but basically the point is that if you do backward, you need to keep like a trace of like your code. So you need to somehow record your code to traverse backward.
I
So I think you can somehow hack so that it's still operator overloading, but I think like source transformation is a bit more natural for backward.
That makes sense. Thank you.